Right. So I want to talk about another thing that becomes pretty important when you're talking about probability. And when you're computing probability, there are two basic ways to do it. One is using rules like the addition and the multiplication rule, which we talked about last time. And the other one is using counting. And the idea behind counting is that if we're looking at probability, the way to compute it is you take the number of outcomes in the event divided by the number of outcomes in the sample space. And that's the probability of that event occurring. Now, the issue is, depending on what type of event or sample space you're looking at, writing out the entire sample space can be virtually impossible. So I want to show you some examples in this particular lecture about sample spaces that are too large to write out, but whose size we can still determine using a couple of counting rules. The first counting rule I want to talk about is called the fundamental counting principle, and that's if you have a multi-stage experiment where each stage is basically its own experiment. So for instance, say I'm rolling dice. So I've got some different dice here. I've got a four-sided die. Four-sided die is just a tetrahedron. It's got, if you notice in the corners, it's got numbers. So on the top corner, I've got a 1. Now if I turn that, you'll see that there's a 1 on the other corners for that particular vertex. And the idea is that the tetrahedron will land on with one side down and it will have a point side up, and that point corresponds to what you end up rolling with the four-sided die. So one experiment or multi-stage event, one event for this multi-stage event could be that I roll the four-sided die. I also have a six-sided die, right? Just a good old-fashioned die. I've also got an eight-sided die, which is an octahedron, and that rolls just like a six-sided die, but it's got these different numbers of 1 to 8 on it. I've also got a 12-sided die, which has a bunch of pentagon faces, has the number 1 through 12, and then I have an icosahedron. Some people call this a D20. It's this 20-sided die, all the faces are triangles, and when it lands, whatever triangle is up is the one that we actually count as the roll. So, if I took the multi-stage experiment, each of these stages, rolling a die, has outcomes and some number of outcomes. So that K1 would be the number of outcomes for the first stage, K2 would be the number of outcomes for the second stage, and so on and so forth. So in this particular example, K1 would be 4, because my four-sided die has 4 different outcomes. It could land on 1, 2, 3, or 4. K2 would be 6. My six-sided die could land on 1, 2, 3, 4, 5, or 6. K3 would be 8. My 8-sided die has 8 different outcomes. K4 would be 12. My 12-sided die has 12 different outcomes. And K5 would be 20. My 20-sided die has 20 different outcomes. So if I want to figure out how many ways I could roll these dice, then all I've got to do is multiply those numbers. So in this particular example, we'd be talking about taking the numbers 4, multiplied by 6, multiplied by 8, multiplied by 12, multiplied by 20, and the number of ways that I can actually roll these 5 dice would be 46,080 ways. Now what's nice about that is I've just figured out how big the sample space is for the experiment of rolling these 5 dice. On the other hand, I've also realized that that number is way too large. There's no way that I could write down all of these outcomes, not in a feasible amount of time. I can also do probability with that, and that's the whole goal behind this. So now, for example, I could say, what is the probability that they're all even? They all land on even numbers. And the thing is, I could figure this out pretty quickly too. The number of outcomes that are even on the four-sided die, there's 2 of them. They can land on 2 or 4. The number of outcomes that are even on the 6-sided die, there's 3 of them. They can land on 2, 4, or 6. The 8-sided die has 4 even outcomes. The 12-sided die has 6 even outcomes. And the 20-sided die has 10 even outcomes. That gives me 2 times 3 times 4 times 6 times 10 different possible ways to roll an even. There's 1,440. So 4680 would be my denominator because it's the number of outcomes in my sample space. And so the probability of getting all even would be 1440 over 46,080. So I'm going to roll the dice and see what happens. Well, I got a 2. Well, this is remarkable. I got a 2 on the 4-sided die, a 2 on the 6-sided die, a 6 on the 8-sided die, an 8 on the 12-sided die, and a 10 on the 20-sided die. It wasn't actually very likely that that was going to take place. The chance of that actually occurring is only 1440 out of 4680. That's like a 1 in 25 chance, something like that. So this is a pretty unlikely event that just took place. And so maybe I should try again to make sure. There you go. I got 2 1s, a 7, a 3, and a 10. So that was certainly not all even. It was just luck. And you guys have to believe me because I didn't actually show you the dice. I mean, I showed you them at the beginning so you can see what they look like, but you have to believe me that I'm telling the truth about this otherwise. Great. All right, so that's how we can use a fundamental counting principle. The next two counting techniques use what's called factorial. Factorial is given by, if I take n factorial, what I mean by that is take that number and multiply by all the lesser numbers until you get down to 1. So here's an example. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So 5 factorial is 120. That is the number of, well, that factorial corresponds to something. Now, the reason why we kind of do this multiplication, you'll see in a minute, and if we kind of think back to that fundamental counting principle from the previous slide, the reason this kind of works out is because if I think about these stages eventually, if the first stage had 4 different outcomes, like those dice, 1, 2, 3, or 4, and the next stage had 6 different outcomes, I can kind of think about building a tree that tells me about that. And the idea is that if I keep on building this tree, and I want to figure out how many branches there are at the very end, well, the idea is that each of these branches will have 6 branches attached to that, and each of those branches will have so many branches attached to it, and so you just multiply those numbers. Now the factorial works out because what will end up happening is we're going to start to see that we've used something and we don't no longer have it to work with, and so we're going to have one less thing to kind of work with, and we'll see that in just a second. So the first thing I want to talk about is combinations. Combinations is when you have a number of objects and you want to figure out how many ways you could choose a certain number of objects from that bigger group of objects. So here I want to talk about playing cards. So I've got playing cards in front of me, and these playing cards we talked about last time, just so you can kind of get an idea. If you haven't seen the last video, we talk about how playing cards kind of work, that there's 52 of them. One of the reasons that playing cards works, or they exist, is because people like to play cards. So when you play cards, an example of a game would be like poker. You take 5 cards out. So you take 1, 2, 3, 4, 5. And these 5 cards would make up your hand. It'd be a 5-card hand. In this particular hand, I don't have anything special. There's no matches. Like a pair would be like a pair of 4s or a pair of 5s or 3 of a kind. I have a 9, 10, and a jack, which start to make a straight, but I don't have the rest of it, which would be like an 8 and a 7, or a queen and a king, or something like that. In fact, this is a horrible hand. Now, poker, in a hand of poker, it does not matter which order you get it in. This hand is the same as this hand. What really just matters is the combination of cards you have at the end. That's why we call what we're about to do a combination. So one of the questions you can ask yourself is how many combinations of cards are there? How many combinations of 5 cards in a deck are there? How many different poker hands are there, essentially? And the way that you figure this out is you realize that if I was to start to try to figure this out, how many first cards could I have? There are 52. So I'm going to kind of start to write this down how I would figure it out without using the formula, and then we'll see why this works out. The number of second cards you could have, there are 51. Third cards, there are 50. You're kind of using the fundamental counting principle. Fourth cards, there are 49 different choices. And the reason why these numbers are going down and that factorial kind of shows up is because you have one less card to choose from each time. So that's the number of different ways to pull 5 cards out of the deck. But one of the things that happened there was that I said first card, second card, third card, fourth card, and fifth card. So there's a problem. This number that I get right here is not the actual number of ways to pull 5 cards out of the deck when you don't care about order. Turns out once you get these 5 cards, there are different ways you could have arranged these 5 cards. So knowing that these 5 cards are the ones that you get, and since this doesn't change if I move cards around, one of the ways I could try to get rid of the fact that I cared about order to begin with is by dividing it out. So I can look at the number of ways to divide out, number of ways to order these 5 cards, and there would be 5 times 4 times 3 times 2 times 1, because there would be 5 choices for the first, 4 choices for the second, so on and so forth. And so this is the number of ways that you can get a combination of 5 cards from 52. Now, that's what the formula does. What we have right here is we have the start of 52 factorial. But there's something missing. What is missing is the 47 down to 1. Now, 47 is 5 less than 52. What really happened was I would have had 47 down to 1, but I would have also had that, if you look at the formula over on the left-hand side, I would have also had this n minus r factorial. 52 minus 5, I'm choosing r, or 5 objects from 52. So if I take 52 minus 5, I get 47 factorial. These would have turned into 1. They would have canceled each other out. And they would have left me with just this part right here. And so this combination formula essentially does what you would think to do if you were trying to figure out the number of ways to take a combination of R cards out of N cards. And the way that it works again is you're going to take, so in this case, from doing 52, choose 5, I'm going to do 52 factorial over 5 factorial multiplied by 52 minus 5 factorial, which is equal to 52 times 51 times 50 times 49 times 48 times 47 and so on and so forth, over 5 times 4 times 3 times 2 times 1 for the 5 factorial times 47 down to 1. But that 47 down to 1 would go away, and I'd be left with this. And then I just have to multiply the 52 times 51 all the way down to 48, and the 4 times 5, 4, 3, 2, 1 to give me the 120. And when I divide those numbers, what I end up getting is there are 2,598,960 different poker hands. Now, the reason I can use this for probability then is that I could ask, what is the probability of getting a royal flush? If you know what a royal flush is, great. If you don't, let me just tell you what it is. A royal flush is when you have 4 cards that are all the same suit, and those 4 cards are special. The king, the queen, so I'm going to shuffle the deck and see if I can get a royal flush. The king, the queen, the jack, the 10, and the 9, all the same suit. Now, since there are only 4 suits, then that means that there are only 4 different ways to get a royal flush. And so, since there are only 4 different ways to get a royal flush, the probability would be 4 out of that gigantic number, 2,598,960. So again, I'm going to just shuffle these cards up a little bit more. And here we go. Card number 1. Queen of Diamonds. Oh, King of Diamonds. 9 of Diamonds. So far I've got a royal flush. Can I get the 10? There's a royal flush. Oh my God, what are the odds? Pretty likely if you're able to cheat off camera, which don't do when you're taking an exam. Don't cheat off camera. You won't even be on camera, but anyways, the probability of getting a royal flush is remarkably small. The next one I want to talk about is what if you do care about order? And if you're looking at cards, you might wonder, why would I ever care about order for cards? Well, you typically don't. But there are things that you do care about order for. So I've brought along some of my collection of Matryoshka dolls. So I've got these different Matryoshka dolls, and I've actually got 15 of them that are downstairs on a shelf. And I got 2 new ones today. The 2 new ones that I got were actually these 2. And on the shelf, I've got 15, but on a smaller shelf, I might only be able to fit 4. Now, it does matter to me which order you put my Matryoshka dolls in when you're talking about actually organizing these. Now, if order matters, then I don't have to divide by the extra factorial stuff. I don't have to divide by the r factorial. So for that reason, if I want to take the 15 Matryoshka dolls that I have, and I want to look at the ways that I could choose 4 of them, but care about the order. So I take my 15 Matryoshka dolls and I randomly select them, and I care about which order I place them on the shelf. Then the number of ways that I could do that would be there are 15 choices for the first one, 14 for the second one, 13, and then 12. And we call that permutations, or 15 permute 4. And the formula here is telling you how to do that. It is 15 factorial over 15 minus 4 factorial, which is equal to 15 times 14 times 13 times 12 times 11 times 10, so on and so forth, over 11 times 10 times 9 times and so on and so forth. Now the 11s down to that are gotten rid of, and you're left with that 15 times 14 times 13 times 12, which is kind of what we might expect. And again, you would want to write this out. There are 32,760 ways that I could do this. I have 15 Matryoshka dolls, which I do, and I randomly order 4 of them onto a shelf. I could do that 32,760 different ways. So if I do 1 a day, it would take me a hell of a long time to actually get through all of the possible ways to order my Matryoshka dolls. So these counting techniques are really good for when you're trying to do probability, because it allows you to count the number of outcomes in the sample space or in the event, so that you can divide those numbers and actually get the probability of that event. One of the things that drives people nuts in this section, or these sections, is there's a particular problem about movies. Now, I'm not doing movies today, I'm going to do books. And the problem kind of goes something like this. Suppose that I go into a bookstore and I'm going to buy 3 books. And I've narrowed it down to 7 books. So I've got The Lion, the Witch, and the Wardrobe. I've got Tris, which is Brian Jacques' book. I've got Marl Fox, which is another. These are all science fiction books, these 3 are. And I've also got it down to Tim Russert's The Wisdom of Our Fathers, The Glory of Their Times, which is a baseball book, MODOK, which is about an elephant, and All Creatures Great and Small, which is about animals. Now, the last 4 books that I showed you are all memoirs, or real-life stories, and the first 3 books are science fiction. So I go to this bookstore, and I see that I narrowed it down to 7 books, but I only want to buy 3, because it's how many I plan on taking home. And so then the question I can ask myself is, what is the probability that when I randomly, because I got it down to 7, and I can't just pick the 3 that I'm going to take home, so I'm going to leave it up to chance. But I'm kind of curious, because I have more memoirs than I do science fiction in my selection of 7. What's the probability that I take more memoirs home? In fact, what is the probability that 2 of them are memoirs and 1 is science fiction? Okay, so in order to do that, I've got to figure out the number of ways to do that. The number of ways to get 2 memoirs and 1 science fiction, divided by the number of ways to select. Select 3. This is like a lot of problems that seem to drive students nuts, so I want to talk about how to do that then. Now look, if I know I want to choose 2 memoirs, so I know at the end of the day I'm going to randomly select 3 books. But if I know I want 2 of them to be memoirs, I could figure out how many ways I could choose 2 memoirs. So what I could do, take the science fiction books, set them aside, and I could just look at the 4 memoirs. And I say, how many ways could I choose 2 books out of the 4 memoirs? Where I could do these 2, or I could do these 2, or I could do the 2 in the middle, or the 2 on the sides, or I could do these 2, or I could do these 2. There's only so many ways I can do that. In fact, I'm trying to choose 2 out of a group of 4. So the number of ways to do the 2 memoirs would be 4, choose 2. That's it. 4, choose 2 is the number of ways to choose 2 memoirs out of the 4 memoirs that I've got. And the number of ways to choose 1 science fiction book out of the 3 that I've got is it could be this one, or this one. 3, choose 1, which happens to just be 3. So now, if I know the number of ways I could choose the 2 memoirs from the memoir books, and the number of ways I could choose the science fiction book from the science fiction books, therefore, if I multiply those 2 numbers, I get the number of ways I could actually choose the books that I'm looking to choose. So that number gives me 18. But I'm not going to do that. I'm going to randomly select them out of the 7. So the number of ways I could select the 3 would be 7 choose 3. And that number is 70. So the probability is equal to 18 over 70. And I get this by using combinations. And I can play the same game with permutations if I care about which order I read them in. Maybe I'm going to randomly select them, and the way that I select them tells me how I'm going to read them or something like that. But at the end of the day, the probability ends up being 18 out of 70, which is about, 9 out of 35. To reduce it. And 9 out of 35, we're talking about just about 1 in 4. So let's see if it works out. I'm going to randomly select. And so far I've cheated you almost the entire time, except for the dice is real. I'm going to randomly select some books. So this one, and this one. All right, I got 2 science fictions and 1 memoir. Didn't work out. So, but at least I'll be reading something good. I got Tris, Lion, the Witch, and the Wardrobe, and All Creatures Great and Small. So I know what I'm reading, and I know what you guys are going to be reading, some more statistic stuff. But otherwise, I'm going to call that the end, and I hope you've enjoyed this probability lesson. I will see you guys next time.